It's really fun when you follow speakers on Twitter, finding out they're going bungee jumping the day before they're supposed to be at your conference. Thankfully, he survived. And still smiling, yes. A little bit taller. Andrew has a whole lot of words that I can't read. Is a member of the Django core team, senior engineer at Eventbrite, original author of the migrations framework, and now he's down south to talk to us about the horrors of distributed systems. Let's make him feel welcome.
Thank you, Katie. And I do have video, but I'm going to refrain from showing you my holiday photos just yet. So this talk is about distributed systems, but a little more about myself, first of all. As Katie said, I'm a Django core developer, and I work at Eventbrite on a lot of their back-end stuff. People ask me what I do there. Basically, everything from Django down, databases, back-end stuff, SOA, architecture, all that kind of stuff. And more recently, I do a lot of work on Django channels, which is what I've become, let's say, infamous for in recent years. And so what I wanted to do here, like last year at DjangoCon Australia, I gave a talk about channels. This year, I wanted to give you a bit of a different talk, and it's about the more general problem. Channels is part of a set of tools to solve a bigger problem of distributed systems. And I want to describe to you like some of the problems you encounter when designing those, and things that when I was designing channels and some of Eventbrite systems and SOA that you sort of start coming across. So first of all, they're really hard. If anyone tells you that distributed systems are easy, or they're plug and play, or they can sell you one in a box that's going to work like magic, walk away from them. They are lying to your face. They are one of the hardest things in computer science, apart from naming things and cache invalidation and all the other jokes. But they're really nasty. And so this talk is going to come in two parts. The first part is why computers hate you, a myriad of ways in which they make your life hell. And the second part is how we can turn these things you're probably familiar with into problems in distributed systems in particular. So let's start out with our first particular thing, which is non-binary failure. This is my personal favorite bugbear that I always try and catch out junior developers with in sort of a slightly weird way. But the idea is people believe that either something works or it doesn't work. This is the wonderful world that, as programmers, we live in. We're like, well, it's great. Like, either my database is up, and I can query it, or it's down, and I can't talk to it, and I show an error page. What you don't consider is that it's a spectrum. There is, at one end, fully up. There is, at the other end, fully down. But there's many, many things in between. And so I'm going to discuss a couple of those ways that come up in particular cases and why they're nasty. So the first one that's very exciting is disks and RAM. So hands up if you think when you write a file and read it back, it's going to be the same. Good, you've all learned already. Oh, no. So one of the fun things about modern hard drives, and SSDs in particular, is that SSDs, because the technology that makes them work is a little bit strange. It involves electrons captured in quantum states and yada, yada, yada. What this means is they're quite susceptible to bit flips, which is where one of the bits in a file flips from 0 to 1 or 1 to 0 after a certain amount of time. And SSDs do this very quickly. Normal hard drives is about 10, 20 years or so. It's quite a long time. And if you keep them nice and cold, it takes longer and longer. But enterprise SSDs, just a week on the shelf without power, and there's a very high chance to have at least one bit flipped. Even consumer-grade SSDs, so like the enterprise ones, the high-speed ones, they flip more often. The ones in your laptops, leave them off for like 3 to 6 months, and at least a few of the bits in them will have flipped from 0 to 1. Which ones? You don't know. You can't work it out. But some of them will have. And so bit rot is real, people. And it happens. And this is not just SSDs. Every technology has this. SD cards and flash cards, the same basic technology, have this as well. CD-ROMs are much better for this. Like the longest kind of technology we have right now is Blu-ray, believe it or not. A good Blu-ray disc kept in a nice sealed thing will last about a century or two, we think. But even then, it's not great. But the other thing that's much more real is memory. Now, often you're not writing things to disk and reading them back straight away, but you are using memory a lot. And one of the big things you've probably heard about is ECC memory, error-correcting memory. Why do we have this? Why is it so expensive? Why do we need to waste money on it? Well, it turns out there's a good reason. Google did a big load of research on their data center, and they worked out that if you have non-ECC memory, like you have on all your normal computers probably, you get 1 bit flip per gigabyte roughly every 2 hours. They have it in a different unit. I've tried to turn it for you here into more reasonable formats. What that means is if you have a server with 32 gig of RAM with non-ECC memory, one of the bits in there is flipping every 4 minutes. It could be somebody's password, hopefully not. It makes it more secure, though, right? It could be somebody's picture. It could be something like a bank balance. And so these are things like you can't just assume that a file either is there or it's not there, or even that like the checksum you're using is correct. You're going to make sure that like, oh, there's double and triple redundancies. And my favorite thing in this is the network. So who here assumes that if they can't talk to the server, the network is down? Oh, you're learning too fast. So a lot of people are like, oh, we have a health check. The health check's going to go, I'm going to try and ping the server. If we get a response from the server, we're going to call it up. We're going to use the server. If I don't get a response from the server, it's going to be down, and we're not going to use the server. Like, well, that's lovely. That's great. Except, of course, when there is a very high latency to the server. Let's say it's about a second or two latency. Your pings still return. Your code thinks it's there. Your website will try and run. But if you're trying to do like lots of queries, let's say you're doing 100 SQL queries. It's a bad move to start with. On something that's usually like 10 milliseconds latency, and it climbs to just 50 or 70 milliseconds, your site can take ages and ages to render. And this is one of the things that really gets you because it cascades and has bigger and bigger effects the further you go. If you've got like a big service-oriented framework with lots of microservices, and you've got lots of deep queries through the microservices, this cascade effect amplifies each layer down you go if your network is unreliable. And there's other things too, like packet loss and bad neighbors. Bad neighbors in particular is a big problem on things like AWS, where sure, you have a virtual machine, but the physical machine that your virtual machine is on is shared with other people. And sometimes those people are very bad people. And so it's common practice these days in some companies to just launch an EC2 instance, test it, see if it's good. If it's not, close it down, find a new one, test it again, just to try and find good neighbors or a good machine. And this is the case too with even Amazon's own stuff. I think one of the outages they had many years ago now, like 5 years ago with EBS, was that their network backplane for EBS, for the block storage for the file system, was sort of weirdly shared with the incoming request stuff, and it got overloaded, and they just couldn't respond to file system requests because they were secretly network requests. Packet loss is another big problem too, as you are all experiencing here in this room with the Wi-Fi. But packet loss is particularly nasty because it can be very variable. You can have really good ping 1 second, and it can massively go away and lose it the next one. And there are some very interesting bugs with networking and like, oh, if it's a certain length. And my favorite story of like, oh, I can only send emails 500 miles, which was somebody having a very short like response time, and like the actual physical length mattered. And this comes under time and space. So you, I presume, all deal in computers, and it's wonderful. And the real world is merely this thing that exists we have to live in and feed ourselves, but computers are the big hot thing. And as part of this, we can happily ignore the laws of physics, because what are they for anyway? A load of scientists in their ivory towers talking about speed of light. Ugh. And in particular, the speed of light might not seem important to you as computers. You're all local. It's in a small box. And that's kind of true. I mean, it's not entirely true. This is a very famous thing from Rear Admiral Grace Hopper. She used to often ask for a nanosecond of wire. This here is a nanosecond of wire. It is the length of wire that a electrical signal will travel in 1 nanosecond. Electricity travels around 2/3 the speed of light in copper. It varies by material, but 2/3 is a good guess for most stuff. And what this means is that, let's say you've got 1 nanosecond here, and you're trying to build a computer that has components more than that far apart. If you're trying to do a clock cycle that's more often than 1 nanosecond, you can't do it. You physically can't get the signal along that piece of wire. And this problem writ large is a problem in distributed systems. You can't communicate with each other fast enough because the wires are longer. And talking about long wires, we're in Australia. And it turns out Australia is very far away from everything else. I got some scientists to check this out. They came back with some numbers for me. So you can see here that Melbourne to US East 1, the most common AWS region, because it's the cheapest one, is roughly 16,000 Ks, give or take, about a couple of hundred. And this means at the speed of light, and this is the speed of light, not 2/3, like purely like we send a signal mysteriously curving around the Earth over to West Virginia, 50 milliseconds one way. That means the minimal time, according to the laws of physics, ever is 100 milliseconds. Now, I opened Slack in a web browser. It made 96 web requests. You can imagine how if that was talking to something in US East 1, it would take about 10 seconds to load. And sure enough, that's my experience. But this is a problem in general, because if you are writing systems that are distributed, it's one thing to have multiple servers or multiple nodes. The next step is when you go geographic. You have multiple data centers in multiple countries. Like trying to make things agree around the world and what's happening, like, is one of the most difficult things to consider. Eventbrite just now is looking at how do we start doing more regional and geographic data. And it's like all of the senior engineers are just going, oh, all the time, because it's a really hard problem to think about. And one of the secrets of distributed systems that they often don't tell you, but it's a good secret, is there is a very easy way to make them work. And that is by having a nice wait period for consensus. You build a system where all you do is you do an operation in different nodes, you send information around, and you try and wait for consensus. You try and see, oh, so-and-so did this, we can all agree and do stuff. This is, in fact, how computers work internally. Like your computers have multiple cores on their processors. Those cores are separate computers, but they happen to be so close they can decide on consensus very quickly. Imagine taking those two multiple milliseconds apart, and it gets longer and longer. You can build a pretty good distributed system if you wait 20 seconds for each confirmation, but your throughput's going to be absolutely terrible. You may as well have somebody just writing on pen and paper and putting postcards in the mail. The other common fallacy that's always fun is that time is the same everywhere. Now, I'm not talking about time zones. Those are terrible as well. That's a whole separate talk. Time itself is awful and wrong. So we have this you may not have heard of him, Albert Einstein. He was a scientist a while back. He came up with a thing called general relativity. And what it means is, without doing a long physics lecture, it means that in order to solve how the universe works, we have to have time dilation, that time runs at different speeds everywhere. And for a while, it was thought to be theoretical, and like it's a bit weird and sci-fi, and then we proved it. Not only do we prove it, every day you have hardware on you that deals with time dilation. The GPS satellites in orbit around the Earth, because they are further out of the gravitational pull of the Earth, experience a slightly different slow of time to us. It runs very slightly, I believe, faster for them. And so because GPS is based on sending you exact time signals, basically the different satellites send you time signals, you work out how far away they are by how long they took to get to you, you have to deal with time dilation. It's one of the big things. And it's not just mysterious physics. Clocks are not accurate. Ever since the 1700s, we started trying to make good naval clocks. The quest for an accurate clock has been ongoing, and it's really, really difficult. Atomic clocks are very good, but if you've seen one lately, they're still like briefcase size. I'm not sure you want one of those to carry around. And so your computer has probably a quartz oscillator. It's pretty good, but as the temperature changes, the frequency of the quartz changes. So you put a temperature sensor to try and correct for the temperature, and you get pretty close, but it still drifts a little bit. And what this means is you can't rely on someone's idea of time being aligned or even being the same speed as yours. And this means a lot of problems that you're like, oh, well, if we were just decide on what time is, we can just have timestamps, and whoever went first wins. Well, it's a great idea until you realize that two people can both go first legitimately in different time-space frames, and duh. At some point, you get like the weird problems of like, you're in a ship and your twin brother is aging slower than you. Thankfully, as programmers now, this isn't a big problem for you. But if any of you ever go to Mars, you're going to have a big issue with this in particular. So now I've given you sort of a brief tour of some of the more spectacular parts of awful bits of computers. Let's talk about how it applies to actual distributed systems themselves. And the most important thing, and the thing that Channels is built around, is communication. And it's what we all rely upon, the internet, services talking to each other, just even in our computers, processes talking to each other. Now, as I said before, networks are unreliable. You cannot assume they will send anything at all in the right order as you sent it originally, or even potentially that it arrives after it was sent in some cases. And so it boils down to basically this choice. And your choice is, how do you acknowledge when messages are received? And the choice is, do you acknowledge them when you receive them, but before you've worked on them? Or do you acknowledge them when you've received them and worked on them and they're done? And this choice boils down to this choice, at most once or at least once. If you acknowledge the message as you receive it before the work is done, you get a case where you can receive the message, acknowledge it, and then your machine dies. And at this point, you've got the problem of, well, we don't know it's finished, and so we just have to go, well, we assume it's done, we'll move on. That is at most once. Your message either gets through because it didn't die in the process, or it doesn't get through, and so you just lose it to time. The alternative is at the end. We have a process that takes the message, does all the processing, and dies before it sends the acknowledgement. And then you didn't get the acknowledgement, so you send it again and again, and this becomes at least once. Whatever your message is gets acted on multiple times. And this sort of basic separation, it's not a binary, is one of the key problems in communication in distributed systems. But of course, it's not a binary. I told you that at the beginning. It is more of a spectrum. The more effort you put in, the better you can get. And people claim to get up here. In particular, quite recently, Kafka put in a brand new system that gets very, very, very close to this with caveats. It's like sort of, it's exactly once, asterisk, 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 and it's like for certain applications that are definable on streams and idempotent and so on. But if you're very cheap and don't really care, you can live somewhere like here or here on the diagram, like, oh, messages sort of get through all the time. But as you get more and more sort of enterprisey and customers complain about things and downtime costs money, you end up getting closer and closer to the middle. And a lot of our research in distributed systems and messaging is how to get close to that middle section. Now, what channels does is it errs on the left side of this graph. It errs on the at most once side, which means that it will occasionally drop a message for you. This is more because of the way that the things it was designed to run prefer that kind of thing. If you think about what the operations are, you think about that difference of at most once or at least once, and the operations that are best suited for them are different. So things like saving some updates to text or liking a tweet, if you do them more than once, that's fine. You can hit like 10 times on a tweet, and we'll just keep storing, yes, he likes it, he definitely likes it, it's fine. That's not really a problem. And so in that case, at least once is perfectly fine. That's the sort of stream of information that we can deduplicate or ignore, or is what we call idempotent, that doing the same thing twice doesn't have any more effect than the same thing once. But there are other things we don't want to do them more than once. In particular, things we do at work, like charging money to people. People get a little bit shirty if you charge them 3 or 4 times, like, oh, it was Kafka's fault, don't worry about us. And so in my case, we are on the side of not doing it. We'd much rather not charge somebody very occasionally than charge somebody twice very occasionally. And that's true of things like sending email as well. And again, this is very much a choice of like, what is your product, what are you doing? At Eventbrite, we have 2 different systems for events, one for each kind. Some things are at least once, and some things are at most once. Channels powers the at most once part, Kafka powers the at least once part. The other part of distributed stuff is consensus, and this is the hard, holy grail part. Talking between computers is one thing. Making them agree, like a room full of programmers, is a very different thing. And not only do they need to agree over an unreliable network with unreliable storage and RAM. Remember, it isn't always the same, and different ideas of what their time is. And this results in a problem that is so difficult that it's probably a whole separate conference. I mean, it is a whole separate conference by itself. I'm not going to try and go through too much of it here. But basically, there's a thing called the 2 generals problem. It's a very famous example in distributed computing. And the idea is you have 2 generals on opposite hills. And they're trying to send messages to each other to decide when to attack. But the problem is between them is a hostile network. It's the enemy. And so they try and send messengers through the enemy and they might not get through, they might get through. They have no way of knowing. You send them into the ether and you don't understand. And you can show that it's basically impossible for them to decide on a time because of the unstable network. You can't, well, did the message like get sent through? Was it right? Like, how do we elect who's leader? Like, if I send a message to Tim saying, hey, I want to attack at 10 a.m., and I get a reply back, was that a yes? Was that a no? Did they see it? And so it becomes a really difficult problem. And it's not just something for big distributed systems. It happens to you as well. There are very real-world examples of distributed problems happening to small projects. And a couple of my favorite examples here, replica lag. So databases have replication lag. So say you have a main database, MySQL or Postgres, whatever your fancy is, and you have replicas of that database. And the replicas, because of the way they sort of consume from the main database, they run behind by 10 milliseconds to a second. It varies a little bit. And let's say that what you want to do is you have some celery tasks that say index new files you upload or like do thumbnailing. And so you upload your file, you write to the main database, and you fire off the celery task. Now, if you're unlucky, the celery task will pick up and run before the replica has got the copy of the change you made. Like you can imagine that celery could do it in 10 milliseconds, replication takes 100 milliseconds. And then suddenly you've got your celery task is running basically behind time. It's like in the past as far as you're concerned. And so the thing you just saved isn't there. This happens even outside systems, like webhooks, for example. At Eventbrite, we had a problem where we send webhooks. You can say, I want to have a webhook sent to me whenever I get a new ticket sold, for example. And we had this whole system done. It was really great, built by me, of course, but maintained by my colleague Bartek, who's much better at it than I am. And it was so fast that it was sending webhooks before the replication lag had happened. And replication lag at Eventbrite is usually under a second, but occasionally spikes to 2 in big on-sale cases. And we were getting cases where people were getting sent the webhook, they were receiving it, sending us an API request, and getting the API response given to them before the replication had happened. Everything was working that fast. And you just can't solve that. You can't pin things in that situation. The other thing is things like timestamps. It's very common to say, oh, we're going to put some timestamps into these database rows to decide the global ordering. Now, I may have mentioned before, time is not a thing. Time is merely a concept. Welcome to my philosophy lecture. And so if you put timestamps in, they'll roughly agree. As long as you're OK with that, you're fine. If you want absolute ordering, you have to have a central time source, a single server you send it all through. A common way of doing this in Django is having the database write timestamps rather than your application. Because often your application is on 4 or 5 or 10 or 50 machines with different clocks and different speeds. But your database often has one master database. And that's the one that you should use the timestamps on the clock from. And this is one of the sort of many things about engineering, right? It's trade-offs. Fast, cheap, and good. Pick any two. If you want all three, then you're completely delusional. And this happens too in distributed systems. And one of the most common things here is databases. We have what's called the CAP theorem, which says that a database or a data store in general can be any two of these three: consistent, available, or partition tolerant. That is, consistency is that if you ask different machines of the same database, they'll give you the same answer. Available is that if you ask a machine, it's always going to give you an answer. And partition tolerant is if you take machines, divide the network, and join them up again, data isn't destroyed in the process. You usually always want partition tolerant. Otherwise, whenever you have a network separation, stuff just vanishes. It's not a great solution for most data. And so your choice ends up usually being consistent or available, which is, do you want it to always be there and not always agree with you? Or do you want it to always agree, but not always be there? Postgres is usually considered to be consistent. And something like, say, Cassandra will be always available. Like, you can read 2 different servers in Cassandra for the same key and get different values back for a short period. And this is one of the things, like, all of distributed stuff is full of trade-offs. And I only have half an hour. I can't give you a full rundown of what to do. But I'm going to try and give you a few tips around like, how to think about these systems and where to start looking. If you find yourself coming to problems that look like these kind of problems, what to start thinking about. So first of all, the most important thing is defining interfaces clearly. It is easiest to think about a distributed system when it is in separable components, when you can reason about components by themselves and then just take them as a black box, zoom out, and consider how they interact. If you have a million lines of code with no clearly defined boundaries, you're going to have a hell of a time trying to debug it. If you have 10 pieces of nicely compartmentalized code that have defined interfaces, working out what the problem is much, much easier. And a big part of all the design of these big systems is how do I separate these things down? How do I make components and make them talk to each other? One of the big things of channels is making it easier for things to talk to each other and understand, like, hey, I'm passing messages around. I want to do this over here, and having Django be one of those parts. The other thing I've mentioned in a couple of slides before is that product and design is a big part of this. When you're making trade-offs, one of the trade-offs you get to make is how your application is designed. It might be the case that there's a very small tweak in the design, like if we don't show an accurate user count here, we can save like 10 seconds on the back end. And the best thing to do is work with your teams of product managers and designers and anyone else who's involved in those decisions and have a holistic approach to just trying to solve the whole problem. Like have everyone sit in a room and work out how we can best solve these things in one big go. I've seen situations where we've got a design through and the design would be near impossible to implement as it is, but a couple of small tweaks and it's like doable in about a week. That's sort of stuff where you can sit there and go like, well, do we need to show somebody this thing straight away? Because if we don't, we can be inconsistent. Do we need to show them this thing? Do we need to give them a particular value? So for example, the webhooks example I told you earlier, what we're going to do, what we're doing, is just delaying all the webhooks by 5 seconds. Because you don't care if you get it like 5 seconds late, but we know how long our replication lag is. And so if we just give you the webhook 5 seconds late, you come through to the API and it's solved. And that's the case with like the product design is changed, sure, but it's perfectly fine. We asked people, they're happy with it. It's still pretty fast for them. And it made the engineering much simpler. It's like there's literally like a time.sleep in there, basically. It's much, much easier to do than like, oh, this crazy system of synchronizing and pinning. And finally, don't reinvent the wheel. Now, I know I'm very susceptible to this myself. It's great to go, oh, it's a really hard problem. I could just write one from scratch, be so clean and lovely. And sure, you could do that. And I encourage you to at least try it, because you'll learn a lot trying it, but don't try it and then use it in production. Try it on your own time to do your own stuff with it, because that's the way you sort of learn and grow. Like I used to do things like make Minecraft servers to try and learn about like high volume networking stuff, because like at some point nobody really cares if it goes down for 5 minutes. And distributed in particular is full of really hard problems. Some of the greatest minds in computing are working on solving like consensus and communication and how to have agreement. And there are algorithms for this that are long and complicated. And if you do one part of them wrong, the whole thing blows up in your face. And so unless you are feeling particularly, say, I don't know, self-flagellatory, don't reinvent it. Go and find some software that works. Go and build on things like Cassandra or React or Redis cluster, if that's your sort of thing. And you can take things underneath, build on them, and if you do become big scale, if you do become a big site that has its own specialized problems, then you can go back, take that bottom layer, and make it more specialized. But most of you are never going to be Google or Facebook or any of the big sites. And so don't try and make your own magical database that's distributed. If you do, good luck. And that's it. So yeah, basically, they're hard. I hope you learned a little bit about what to do with them. And thank you very much. Hello.
Hello. If I have enough lag, will this work?
Yes. Thank you very much.